Good afternoon, everyone. My name is Byron Cook. I'm really excited to introduce the speakers for the next session. So this is a talk by three members of staff at Goldman Sachs, Kai, Sujoy, and Victor, and they're going to talk about their use of some tools to solve a problem that they had in Goldman Sachs using tools that come from my team. We thought that before I hand over the mic to Kai that it might be useful for me to give a little bit of background and context around the subject of this talk. So I thought I would do that. So this talk is in the space of what we call provable security. This is an initiative that we have going on at AWS to use formal methods, logic, formal verification, automated reasoning, whatever you want to call it, to attempt to prove properties about programs, networks, policies in order to establish the highest possible level of security and to lower the cost of establishing compliance certification. So this is an investment we're making in AWS, and we're doing this work at both levels of the shared security model. So customer facing, we have a couple of services coming from my team, one called Tyros, one called Zekova. So Zekova is something we'll hear a lot about today, so I won't talk too much about it. Tyros is a tool that helps customers understand the behaviors of networks that they're building on AWS. And these are not GA services, but these are services that in some cases customers such as Goldman are using in a beta form. But furthermore, these are tools that do empower a lot of existing AWS services. So Inspector, Macy, Config, S3 Console, IoT, Device Defender, et cetera. So that's for helping customers be secure in the cloud. And then we're also using these same techniques to harden the foundations of AWS. So for example, we're proving the correctness of crypto in use at AWS, proving the correctness of pieces of the virtualization stack, for example, the bootloader. And then we're using a lot of these techniques also to change how we're doing compliance in AWS. The big idea of this work is that when trying to reason about programs, so programs typically have an infinite or unbounded amount of possible state. So we're trying to reason about the infinite, and we're trying to do that in finite time and space. These problems are formally undecidable, or if they're not undecidable, they're intractable, right? So they're NP complete, they're P space, or they're undecidable, which all sounds very scary, but it's not as bad as it sounds. So what that undecidability result means is that if you're using tools that can reason about programs or reason about intractable or undecidable problems in the area of program verification, we have to acknowledge that in some cases, the tools will fail to find an answer. So the tools can usually provide an answer and tell you, yes, this program is correct, or no, this program is not correct. But in some cases, they will either run forever or return an answer saying, I'm not able to find an answer. And that's because of this foundation of the undecidability of the problem. And so what we're doing in AWS is looking to build heuristics that lowers the occurrence of that failure down to some acceptable level. And we're also looking to apply these techniques to niche areas where they're going to be especially successful. And so Zekova is the one we're going to hear most about today. So this is the application of automated theorem proving techniques to answering questions about the semantics of IAM and resource policies. And formally, this is a P-space problem, but Zekova, which is the implementation which uses automated theorem proving, always answers the questions in less than a second or two in our experimental results. So while it's formally a P-space problem, it feels like a P-time problem because of the heuristics that are implemented using the automated theorem proving. So if you'd like to know more about this area of provable security, in particular provable security at AWS, there's the Provable Security webpage. This webpage has pointers to talks. It has pointers to blog posts, and it has pointers to research papers. By the way, the this talk will be available on YouTube, I think within 24 hours, and also on SlideShare. So if you have failed to take a photograph of that URL, it'll be available to you soon. Furthermore, I will be in the security booth at 4:15 if you want to ask me questions in person. Oh, there's a couple of talks. There are 3 talks. If you like this talk, you might find these 3 talks enjoyable also. So there's a talk by myself and some folks from Coalfire and Chad Wolf from the compliance team in AWS about the use of these automated reasoning provable security tools to change how we're looking to establish compliance certification within AWS. There's a talk by the AWS customer LogMeIn also about their use of Zekova to solve some problems that they had in their enterprise. And then there's a talk by the Inspector team about the new Tiros-enabled feature within Inspector, which allows customers to reason about the possible behaviors of networks that they're building on top of AWS. And then finally, if you like automated reasoning logic, formal verification, and you want to know more or meet more people who are doing this kind of thing or are interested in this kind of thing, I welcome you to the Automated Reasoning Lounge, 10 till 2, at Encore 5 on Thursday. And with that, I'm going to hand things off to Kai, and she'll begin the proceedings.
Thank you, Byron. Hi, I'm Kai Huang. I work in public cloud engineering at Goldman Sachs. Today we're going to talk about our use cases and cloud adoptions, the challenges we face, how we leverage AWS Zekova to solve those challenges, and how we implement this at scale. So first, a little bit about who we are. Goldman Sachs bring people, capital, and ideas together to help our clients and the communities we serve. Innovation's at the heart of Goldman Sachs. Part of our business principle is that we regularly receive confidential information as part of our normal client relationship. This is why we're talking about security and policy verification today, because to breach confidence or to use confidential information improperly or carelessly would be unthinkable. So what are some of our use cases? Today, we implemented a secure extension of our internal provisioning and management system that we provision for our internal compute. And we built a secure extension to AWS, and that let us leverage the liquidity and capacity that Amazon offer. We mainly leverage this for our grid computing and general computing purposes. We also have other use cases like lift and shift, where application stack internally wants to move their application out to AWS, whether to be closer to geographic locale of their client or to isolate dependency they have with internal systems. New innovations. As you guys heard today at the keynote, there are a number of really cool things coming down the pipeline that AWS offered. Developers are excited and want to learn, try different technology stacks, new data analytics, new databases, new machine learning services. They want to learn and play and be able to build better applications to serve their business. Business continuity. In the event of data center outage, different natural disaster, having AWS available as a place where we can move our workload, help us continue our business and make our business resilient. So with all those different use cases, there are also different objectives, right? Developer wants to feel empowered, enabled. They want to be able to build, learn what they need to do, build what they like, and build cool apps. Right? Business, on the other side, wants to have agile delivery of the product and the service, get their product quickly to the clients. On the enterprise IT side, we have to balance things like management and governance across all the different use cases, as well as scaling, because we have thousands of developers, and we have thousands of applications. We decided to embrace the scale. So we adopt AWS organizations. In fact, we have multiple organizations. And we decided to say, adopt the micro account architecture model, where each developer gets an account. They get to learn and play in a very isolated sandbox in an isolated AWS organization that is not connected to network, where they can basically build what they like and figure out what a different technology stack suits them. In that model, we also build a set of management accounts. These are accounts for account creations, managing security centrally, billing, logging, and share services like Direct Connect. And we also take the same blueprint model to our business application stack. So similarly, for our business application, we set up another separate organization where each application by its environment get allocated an AWS account. And we also set up the same management model for the enterprise IT to manage centrally. So why did we decide to take the micro account architecture model? It's really, an AWS account provide a very well-defined boundary. Per deployment environment within a single application helps you limit blast radius. Something that goes wrong in a dev account does not necessarily impact anything happening in your production account. It also helps us with billing, because if you tie an AWS account to an application and its environment, any charge incurred, you can charge back to that application specifically for that business. And it's a very clear separation of function for enterprise team as well. The application team manages their account, enterprise team manages from the management account. There are, however, a lot of challenges. Different applications has different security requirements. Right? And we need to apply security policy in a flexible way and enforce them while allow them to scale. And there's also decentralized traditional security policy and monitoring. Traditional security policy and monitoring tend to be on an aggregated central place. Now you're pushing down to enforcing them at the account level. So let's take a look at the challenges in a specific use case. So a user, so for example, an administrator for the application production account, wants to block principal for another account, say the dev account. They want to separate dev from prod. They want to block developer, then principal from the dev account, accessing a S3 bucket in production account. And they set up this S3 bucket policy. How many people, raise your hand, see something's wrong with this S3 bucket policy? Cool. How many people, raise your hand, see nothing is wrong with this bucket policy? And how many of you don't know? Okay, so that bucket policy actually does not calculate back to the intent that the administrator expected. That policy actually allows access for everybody in the world who is not principal in that dev account. This means that everyone now has access to the users, that production account bucket, including anonymous, unauthorized users. Now, looking at a single bucket policy, you can look at it and say, hey, something is wrong with that. You can kind of apply logic and reasoning about it by examining it manually. However, how do you apply this kind of reasoning across hundreds of accounts and potentially thousands of buckets, thousands of IAM policy and resource policies? So you need an automated tool. But before we get there, let's do a little bit primer on satisfiability modulo theories. So this is in the computer science and mathematical logic domain, is a constraint satisfaction problem, where, take a look at this example. For all values of x and y, is x plus y greater than x minus y? So once again, raise your hand if you think this is true. Okay, raise your hand if you don't think this is true. And raise your hand if you don't know. Okay, so well, if y value was negative, that constraint would not be satisfied. But to satisfy that constraint, you can say, assume that y value is positive. Now, an SMT solver will respond that, hey, this formula is true for all values of variable x and y. So enters AWS Zekova. So Byron's group in automated reasoning implemented an analysis tool that built on SMT solvers, translate policy into a mathematical formula, then compares. So back to our S3 bucket policy example earlier, what Zekova does is translate that into a mathematical formula. It now says resource equal to, here's the ARM, the bucket name, and principal not 112233. This makes it much clearer to reason about. And because it's a mathematical formula, you can now do operations like comparison. So you may see this already today in S3 console, where Zekova compares the user policy defined in a bucket against the world-readable, world-writable bucket policy. So it compares if the user policy is more or less permissive. It is more permissive, then Zekova flags the policy as allow public access. This is where you see little yellow flags say public in the S3 console. So how does this help enterprise? Well, because Zekova gives you ability to do comparison, you can build a custom-defined baseline to compare what do you have running in an environment. Does that meet your baseline? So for example, a number of companies would want to make sure that their buckets are only accessible by the company. Right? You don't want your buckets to be accessible by your competitor's company where you're storing your data. So you can define a baseline policy to allow only the company's account. And you can compare that user policy with the baseline. If the user policy is defined in the running the account is more permissive, then that flags this issue. So taking that, and let's bring it back to the enterprise. So at Goldman, we have a concept of application inventory. And the application inventory defines the requirement and metadata about an application. This inventory describes the business unit, data classification, whether the application is classified as confidential, PII, or public, the dependency that the application has, the entitlement and additional entitlement store that application has, as well as the environment. And we call this a deployment. So internally, we already have a concept of deployment. Say you can have a dev deployment, a QA deployment, UAT deployment, and production deployment. And an AWS account is simply represent yet another environment for the application to deploy within. So we represent AWS account as just yet another deployment for the application. And the same classification, the policy, and the requirement applies to AWS deployment. We also extend the application inventory management system to include additional things like access intent. Right? Is this application intended to be accessed externally or by vendors or only within the company? So this helps you apply the traditional least privilege principle because now you have ability to define what the application characteristic is, so you can derive the baseline that you need to apply for the application. So because we scope the application to its environment as a deployment to an AWS account, we can tie that back, say when we're evaluating that AWS account, look back to the application inventory and say, all right, given this application, this profile, what are the baseline policy I need to compare? So AWS IAM policy and some resource policies like KMS policy are default deny. So you only need to set allow statement. So in your environment where given an application resource must be accessible by the application, if the application scope to an AWS account with entitlement declare, this is all defined in the application inventory, then AWS resource must allow the account itself and the declared entitlement. So let's take an example of use case here. So the application says, hey, all my data must be stored encrypted. Environment separation must be enforced. And production data must be only accessible by production application. So the adopted pattern that application take is they use customer managed key from KMS to encrypt application data. They set up AWS config rule to check if, in fact, the bucket is always encrypted. Right? Then they have application role declared entitlement under application inventory. So to look up and say, hey, is this key policy set up correctly, or is the IAM policy set up for access to key? Then it's simply a lookup to say, what is the baseline, and compare with what's running in the environment. So comparing user-defined policy here, what the user actually defined in their environment, they end up defining, say, hey, allow use of key, here's my production account, here are the roles, here my QA account, here are the role and dev account. And the application baseline, by looking up the inventory, is, well, this application is tied to this application account because we look up based on the inventory, and the role declare based on the entitlement declare, and we send that to Zekova to compare. And Zekova to return, in this case, it's more permissive. And this will flag, say, hey, something is wrong with this policy, notify the users or notify the application team so that they can remediate. So the use case of Zekova is that it gives you the micro level verification that you can check on each of your resources against the intent of the application. And it allows user to automate that verification at scale. This complements with other IAM tools like service control policy, which lets you do macro level enforcement to control what user can or cannot do. So at this point, I'm going to turn over to my colleague Sujay Saha. We'll talk about how we implement this runtime verification at scale.
Hi, everyone. I'm Sujay Saha. I'm a software engineer at Goldman Sachs. And today I'll be talking about how we're enforcing runtime verification at scale and how we are leveraging Zekova to do so. So at Goldman Sachs, we have hundreds of Amazon accounts, and they're a good mixture between developer sandboxes and accounts that run production workloads. Now, this makes the ability to analyze and detect the security posture of the account and make sure that it's compliant to all our firm standards. Because we have a lot of accounts, and on top of that, we have to inspect each and every region. Now, in order to meet that goal, we had to come up with an event-driven approach that would be able to not only detect whether or not the security posture has been compromised, and if so, it would be able to take action on that. So in order to do so, we decided to set about this process by segmenting out our work into 5 different topics. The first one we wanted to achieve as part of this process was to aggregate data across different Amazon accounts. This including turning on various Amazon services like config, CloudTrail, and other resources that we could use to collect information about the account's security posture. The next step was to centrally process and analyze that, and especially look at things such as IAM policy and validate that to check if they are compliant to firm standards. And if not, we would, at the third stage, keep some form of record in form of a database where we could keep track of all these events that are non-compliant and take action on them at a later time. In parallel to that, we also wanted to make sure that all the non-compliant events that we are detecting, we should have a way in which we can classify that and make sure that we can assert different risk levels to those. For example, in case we detect open public access buckets where there's confidential information kept, those are considered high-level security risks, so they will be classified as such. And downstream services would be notified on taking action on those, or the user would be notified as well. In addition to that, we know that as part of this conference and over the year, Amazon releases many new services, and we would want to make sure that our application is modular so that we can support these services and take them as data sources so that we can further enrich our application in order to determine our account security posture, as well as support vendor products in this space as well, who would also give us information. So in order to set about doing this project, we looked at a number of different products, and we narrowed it down to these 10 building blocks. So as I said, we wanted to have an event-driven approach in which we wanted to handle this situation. So we took AWS Lambda and a suite of AWS Lambda and step functions to create our central application that would respond to, that would do things such as investigate the security posture of the account, as well as take action on those. The next thing that we did was looked at a suite of Amazon services that provide logging, for example, CloudTrail and config. In case of config, we enable config snapshots across all accounts and all regions, and we made sure that we could receive all the configuration snapshots into a central location where we could process them. Similarly, we did the same with CloudTrail. And apart from that, we also enable flow logs, which is also another logging service that would inspect network security traffic, and we could use that as well as part of our project. In addition to that, there are other security tools such as GuardDuty and Macy that we considered as data sources. These are great because they can provide us cases where the user is unaware of events that are happening that might be beyond their control and where some resources might be compromised. So these could provide a good source of raw security alerts that we could process. In addition to that, we use Zekova to obviously do policy validation at scale. And finally, we use DynamoDB as a central repository to store all our different non-compliant events that we were detecting. So here's our overall architecture from the building blocks. So as part of, in Goldman Sachs, we have, as Kai mentioned, segmented our accounts into different categories, right? We've got the client accounts that are like accounts that are used as developer sandboxes or production accounts, right? And on top of that, like in an Amazon organization, we have a concept of management accounts where we have things like logging account and security account. Now these allows us to curate all things related to logs, for example, in the logging account, and all security-related events in the security account. So, and in order to do that, firstly, in the client account, we have to enable various things such as the ability to collect different raw security events in form of like Macie and guard duty, and all logging events that are collected by CloudTrail, Config, and flow logs. So in case of the logging account, we actually downstream all the events that are captured in all child accounts and across all regions into central S3 buckets. And from there, in the logging account, we've got a Lambda function that will actually inspect all the different configuration snapshots, CloudTrail activities of the user, and be able to determine if those things are compliant to firm standards or not. In case of config snapshots, we actually use Zekova so that we can inspect the IAM policies and resource policies to be able to determine whether or not they are meeting our standards. At this stage, we will process those events and be able to classify them as compliant or non-compliant. We'll forward those events to the second stage, Lambda function called the risk classifier in the central security account. Now, the risk classifier's job is pretty simple. It receives processed events from the logging account, where like we have classified the different things related to all things logs. And it'll also look at things like Macie and guard duty events to be able to determine if these events need merit action, or they can be sent as warnings to the users at the downstream. So at this stage, we will classify these different events that we receive into different risk categories, and we'll store that in DynamoDB, where we can use the streaming API to take action on that, or we can use that later in a way in which we can, whenever we resolve these incidents, we can keep track of all these events. Finally, we will also in parallel to this, we'll also send out alerts to the user and other downstream services so that they can take action on that. And we can keep our design modular so that we can have more services listening on at the very end. In addition to all of this, in cases of grossly misconfigured policies or things such as S3 bucket being unencrypted, EBS volume being unencrypted, cases like those, which are gross misconfigurations, we have a set of remediation functions that will take action on the user's behalf and will override the bucket policies, or like in case of EBS volumes, it'll encrypt those or take other actions in that space. This is achieved by a suite of different step functions and Lambda functions. Now, as you can imagine, in order to achieve this entire process, we needed to set up a lot of different services and components at account creation time. This is to make sure that we have complete security coverage from when the account was first created to when the account was finally delivered to the user for any use, or like whatever they take or whatever they use afterwards. In order to do that, we have a set of different Lambda functions that we use to like bootstrap the account. We set up, as I mentioned, like configuration snapshots are taken once every hour for every region, for every account, and streamlined to a central S3 bucket, and things like that. Like we enable CloudTrail, guard duty, and Macie. In some Macie, we enable in only like certain accounts, but in most cases, the first three is what is actually delivered. We use this bootstrapping process continuously to make sure that there is no account drift. As part of this bootstrapping Lambda function, we also have an auto remediation role that is created in each individual client child account. And at this stage, we can use this auto remediation role is what is used by the remediation functions and step functions to be able to assume role into the child accounts and be able to take action on their behalf and override whatever insecure policies that we noticed. Now, at this stage, now that we've covered the overall architecture of our implementation, as well as given like the supporting Lambda functions and other things that we use in this process, let's look at a deep dive of how we are using Zekova to do like runtime policy checks. So, in our current setup, if you can imagine that if a developer is attempting to set up like their VPC endpoint, for example, and they want to set up a VPC endpoint policy for S3 bucket access, right? And the developer is new, he wants to like quickly finish up like some part of the project. He decides, okay, like let me just put the resource as star in the VPC endpoint VPC endpoint policy, and he believes that, okay, like this is fine for now, like we'll take care of this later. The problem with that policy is that it allows the user, like that application to access public buckets, like all public buckets, not just GS provided buckets. And that can be a clear and easy case of data exfiltration by the application, or by mistake it can try reading public buckets which it doesn't have any access to. So cases like that will be detected by the configuration snapshot, which is captured once an hour. It will be forwarded to the central logging bucket, and our first stage Lambda function that's located in the central logging account will be triggered by an S3 event notification trigger. And then at that stage, it'll extract the IAM policy associated with that bucket and will construct what is known as a runtime baseline policy of that. Let me explain what that is. So, as Kai mentioned earlier in the talk, we've got something known as an application inventory internally. Each Amazon account that's created has its own deployment ID associated with that. At our application inventory stage, we have a way of defining what the deployment can have access to. And that is where we can say, okay, this deployment and this account has access to this set of internal private S3 buckets. And at that stage, we can say, okay, like here, what we will do is we will look at the application inventory, we will construct the baseline policy at runtime, and then we will compare that policy with the user submitted policy, where he had like listed as star. And in our runtime policy that we generated, it'll only have, say, a set of private buckets that a deployment has access to. Obviously, when we use Zekova at this stage, the API will return us the answer that the policy supplied by the user is overly permissive and thus does not meet our compliance standards. So that will be flagged and stored in DynamoDB, and then we can take action on that at a later stage. Now, the action that we take on this is, again, by a similar approach, where our remediation function looks at the event in DynamoDB. It sees that it's a bad VPC endpoint policy, and then it will, again, inspect the application inventory, and at runtime, will construct the baseline policy that this has access to, that the deployment and Amazon account has access to. Then it will override the VPC endpoint policy with that particular one, and then it will make sure that that way we'll make sure that we don't have a case where a VPC endpoint has access to all buckets, and it will be like locked down and secure. In addition to this, we'll send an alert to the user so that they can take action on it at a later stage. So from what we've seen, we are able to do continuous formal verification of IAM policies after we do a deployment of our resources. And in addition to this, like using our event-driven approach, we are able to continuously remediate those as and when they happen. And in addition to that, using our supporting functions like the bootstrapping Lambda, we are able to avoid a drift in the Amazon environment that we are using to like extract information and then to determine the security posture of the account. This allows us to make sure that the user doesn't accidentally change their IAM policies and all of that, and that's because we basically rerun the bootstrapping function on a continuous basis at regular intervals. Finally, for cases that are not covered, since we have guard duty and Macy turned on, we can send those non-user initiated events directly to the user, and they are like alerted about that, and they can take action on their own side. And finally, like from our model itself, we can see that if we go back to the diagram, we'll see that this design is highly modular. So if and when Amazon announces new services in this space, like more services to like capture logging information, more services for security, like Security Hub, we can definitely put those in there, and we can use that to like enhance our application, or we can add in more vendor products as well. Cool. So now you might have noticed that this is all a post-deployment model. It's more reactive model than a proactive. We wanted to give developers an ability to be able to know in advance once they're committing, once they're making some changes on their side for like if the policy, if the resources that are committing, are they compliant or not? So in order to like, we made an effort in that space, and like my colleague Victor will talk about that.
Thanks, Sujay. This is actually a great introduction into what I'm going to be speaking today, because the system that my colleague Sujay just explained allows us to do policy verification and policy enforcement at scale across hundreds or even thousands of accounts. But we do this at runtime, right? We want to complement this model in order to also integrate pre-deployment checks so that we make sure that we're closer to a developer, have a faster feedback loop with the developer, and they can be more agile while, on top of this, still maintaining best security practices and our security standards. And ultimately, I'm going to also go over how we integrate. So what I'm going to be going over is our design and how we integrate this model with continuous integration and continuous deployment in order to aid us in this process. Oh, there we go. So before I go into the details of our design, I wanted to give a small primer on infrastructure as code for those that are not familiar. Infrastructure as code is a technology it's a methodology that we use very extensively in the public cloud engineering team, up to a point that we are allowing and encouraging other teams within the firm to adopt this model so that at one point, it becomes the standard for managing infrastructure. Infrastructure as code, all it does, it's a form of configuration where you specify the resources that you want to instantiate in your public cloud environment. Now, within this configuration, you'll specify your resources and the attributes that you want to customize those resources. Now, a certain technology, in our case, we use HashiCorp's Terraform. AWS has an offering for this called AWS CloudFormation. A specific technology would go and parse this configuration, identify the resources that you specified, the attributes that you specified as well for customizing your resources, and the relationship between the different resources, so that ultimately it can mirror them in your public cloud environment to establish the dependencies between load balancer and EC2 instances, S3 buckets, and KMS keys for encryption, et cetera. So this is a diagram that sort of explains that overall process. And as you can identify, we want to prevent any grossly misconfigured infrastructure as code that a developer has developed from ever actually going into public cloud, right? And this is where infrastructure as code, as the name suggests, it can be treated the same way as code. So it can be version controlled so that we have increased responsibility, accountability, and we can also see and track all of the changes that our infrastructure has experienced throughout time. Most importantly, though, infrastructure as code, the same way as application code, it has to go through a building process. And turns out we tweak the definition of what this building process is in order to make it suitable for our standards and for our security requirements, and make sure that the infrastructure as code configuration that is going to go out and provision resources in the public cloud in AWS actually meets our security requirements for that specific application. Ultimately, this building process we're integrating it with our continuous integration and continuous deployment pipeline. So we're closer to the developer, have a faster feedback loop, and they can still be agile in their development for their infrastructure, as well as maintaining best security standards. Terraform has a concept that aids us in this process. It's called Terraform Plan. All it is it's a command for Terraform that outputs the changes that will happen in your public cloud environment. So let's say that from the beginning you started off with an EC2 instance, and you deploy that into your AWS environment, and now you want a second one, and you specify that one as well in your configuration. Now the Terraform plan, all that it will identify is that there's a new instance that it needs to provision. Similarly, if there's a change in an IAM role that you already have existing, a role that you already have existing, you want to change a policy, that will be reflected as well. If you're changing a resource policy, that's also reflected. So we can feed this configuration, this output of a Terraform plan, into what we're calling a policy engine. This policy engine, I want to make myself clear, it's not referring to the resource policy or IAM policies. It's rather our firm's policy, a sort of set of rules that we establish to be security standards and best security practices. Ultimately, we identify the user-defined policies from the Terraform plan, the changes that we're seeing in that infrastructure, in that configuration, so that we feed it into this policy engine that under the hood would use Zekova to leverage that verification and that validation that the policy that they're actually getting out to AWS is meeting our standards. So as an end result, we have that. By the way, by no means this sort of language, that's sort of conveying the information of how a configuration sort of looked like, but it doesn't actually is a real example. But the end result is that if a developer specifies this configuration that of an S3 bucket, they want to specify a resource for an S3 bucket, and within this resource, there's an attribute that specifies that there's no encryption, and the policy, for example, essentially allows everyone to access this bucket. Now, we feed this in to our policy engine, and one of the rules will say, okay, I need to use Zekova in order to analyze this policy. At the end result, seeing that Zekova returns a more permissive result, we give back the user the feedback, an error message to say your S3 bucket is too permissive. Now, hold on 1 second in here. It's too permissive compared to what? This is what you see underneath this policy engine logo. The same way that we're doing it with our runtime environment for policy verification and enforcement, we want to do this as well in our pre-deployment environment, right? So we're leveraging our application inventory very heavily. It becomes very handy to have a lookup table, essentially, of all the security requirements and metadata that an application has to adhere to. And we do this lookup dynamically so that we create this baseline policies so that we can provide it for Zekova to analyze the user-defined policies that you can see in the screen. The system gets brought together at the point that the user, at every commit, at every merge request, or every release, they trigger, as part of their CI/CD pipeline, a building process. This building process interacts with our policy engine that will run through several rules. And within those rules, right, will be that we need Zekova to be compliant to our security standards. So for this, the policy engine will have to use Terraform plan for extracting the user-defined policies. It will have to use our application inventory for also defining the baseline policies for that specific application, and ultimately Zekova, so that we send it to and do that formal verification and break the CI/CD pipeline if there's something wrong with it, right? And give feedback to the user. This way, we're avoiding any misconfiguration to going out into public cloud and successfully meeting and making sure that our environment is locked down. If, on the other hand, the developer did follow good security practices and actually is very aware of their security standards and was able to lock down their IAM policies and resource policies, the CI/CD pipeline is successful. To sum up, actually something that I forgot to mention, this policy and this rules, it's something that is usually called policy as code. So let me get back to it. Users, to sum up, will be able to develop and manage their infrastructure using infrastructure as code. They'll be able to store it in version control so that they can have increased responsibility, increased accountability, and track all the changes that their infrastructure has seen throughout time. Ultimately, at every merge commit, at every merge, at every commit, at every release, they will be able to interact with a building process that we modify, that we customize to our standards, and that underneath is using Terraform, our application inventory, and Zekova for analyzing the user policies and IAM policies. In the end, once this building process is successful, the infrastructure is successfully it's successfully deployed into public cloud environment. And this is where we're gracefully handing it over to our runtime environment and runtime verification and policy enforcement so that we have both sides of the system locked down and in place. And we're making sure that we're upholding our security and our business principles of protecting our customers' data. I'm going to hand it over to Kai for some closing remarks.
Thanks, Victor. So just closing up, what through this journey, what we learned is collaboration with Amazon is key. Working with Byron's team, it's been amazing. They were able to take something very academic and able to translate into a usable, practical tool for us to use and leverage and run at scale. Also, cloud shift. Right? The same security principle as traditional on-premise still applies, but the tooling has to adopt the changes. And the multi-member account management that we talked about today, the runtime environment verification we talked about today, we had to build those tools because at the time it didn't exist. But today, as you heard during the keynote, there's now AWS Control Tower, which can help you with multi-account management, and AWS Security Hub, which is a similar aggregation that we're doing in our runtime environments as well. So the tools has to change and adopt with the cloud as well. There's also a lot of opportunity. There are a number of growing use cases out there. And because we're deriving based on metadata on attribute store and application inventory, right, we have to continuously update, understand that for different use cases and different services, what that pattern should look like depending on the use case, different access intent, and different classification. And it's also continuous user education with our users, right? Cloud's new, cloud's interesting, it's exciting. People want to learn and want to know what the right pattern is. And we want to be able to build out a repeatable pattern for people to adopt. Oh, that's the end of our talk. Please complete the session survey, and we'll be hanging around and come talk to us if you have any questions.